All right. Hello, hello, hello. Good day, all. Today, we're going to be going into free body diagrams. This is going to be the first of two videos. This first one is to give you an idea of how to spot the forces that we're going to be dealing with when we're drawing free body diagrams. The next one will be actually drawing and going through a couple of strategies for that. Free body diagrams are diagrams that we use in physics to help us determine what forces are present in a certain stance. So you have some kind of situation, you need to figure out whether or what forces are acting on some object and what direction they're going to be acting in. So in this video, we're going to talk about what are the key things to be looking for. And then in the next video, we'll start actually applying that to start drawing some free body diagrams. You have seen some free body diagrams already. I drew some in the last one when I was drawing those little pictures with the arrows going wherever. Those are free body diagrams. That's all we're doing. And I have a packet with, I don't know, maybe 36 practice free body diagrams for you to work on. So you should have plenty of practice for those before we get to the quiz. So already mentioned this, free body diagrams. We use them when we're solving force problems in physics. They show the forces. The blue here is your definition that you're going to need. And obviously this is available online, so you can get access to this. That is not supposed to still be there. I need to fix that. This should say there are 9 forces that we're going to be dealing with. Of the various forces that we have talked about, there are only 9 that we're really going to be dealing with on free body diagrams. One of the 4 fundamental forces, all 3 field forces, and all 5 of the contact. Electromagnetic, strong nuclear, and weak nuclear, we're not going to be dealing with. We could do stuff with EM, but we haven't done anything or talked about electromagnetism at all in this class yet, so we're going to save that for physics. So yeah, gravitational force. Basically, gravity is always present. I mean, unless I give you a problem about some space shuttle that's off in deep space, gravity is always going to be present. Okay, on a small scale, that's something happening in Earth's atmosphere, which is going to be 90% of the things you deal with. Gravity is going to be directed down. Okay, gravity is always down. It's pulling you towards the Earth. Okay, we technically, there is a point where we should switch from local gravity to universal gravity, F little g to F big G. We're not going to deal with that in our free body diagrams. We're going to call everything F little g in here. So we're always going to assume that if there is gravity present, that it's F little g. So we're only going to use F little g for our gravity in our free body diagram. So this is the only kind of gravity we'll be using. We're not going to mess with big G. I should mention before I get too far, there is a worksheet to go along with this. The worksheet has one vocab question, which is the blue, and then it asks for how you are able to identify all of these forces. That's the green text here is going to be the main things I'm looking for, but you're also going to need to know several things, several of the other bits. But the green is what I'm expecting you to type on the worksheet. Okay, only field force, I mentioned that already. Okay, so let's go on. Thrust, drag, and lift. So thrust is one that we're going to be seeing a lot. There are a couple things that I mentioned here. Anytime something's being propelled by a jet engine. So any rocket, any plane. Now, technically, there's an argument to be made on like passenger planes, whether that's thrust or not. We're just going to call it thrust for this class to make it easier. Okay? So there is thrust pushing any plane or jet or rocket of any kind. That's always going to be thrust. Okay? That's important because when we start talking about like cars, there is a frictional force, kind of like when you're walking. We talked about when you're walking, there's friction pushing you forward. The thrust takes the place of that friction. In a car, it's going to be friction, again, pushing the car forward. For the same reason, the car is trying, or the wheel is trying to turn, and that's the friction is opposite the direction of that attempted motion. But we're on thrust. Gliders do not have any kind of engine. Okay? Gliders, if you don't know, gliders are planes that you have to tow it into the air. So you literally tie a big long rope from the glider to another plane that has an actual engine, usually a prop plane. The prop plane takes off and flies, and the glider is just pulled along. The plane with the engine gets up real high, they cut the line to the glider, and the glider just kind of goes and does whatever. And as long as they're careful, they can pretty much go not an unlimited distance, but pretty far. Sometimes they circle back and land. Sometimes they'll try to rehook up and rise again. But if they're designed well, gliders will go for a very long distance. But they have no engine of their own. Okay, so there's no thrust there when you're dealing with a glider because they don't have an engine. Now, the space shuttle does have an engine, but when it's entering Earth's atmosphere, it's out of fuel. So it doesn't use any engine when it's coming in for a landing. So if we have a space shuttle problem, that space shuttle is acting like a glider if it's re-entering Earth's atmosphere or if it's coming in for a landing. Okay, there's no thrust there. It's just coming down and landing. Okay, then we have drag. Drag, we said, is basically just air friction. So anything moving through a fluid is going to experience drag. But that drag is not always going to be measurable. When you are walking around in the school, in a classroom, okay, when you go to get a calculator, when you walk to the bathroom, go to the library, okay, you are technically experiencing drag. But the density of the air is so low that you don't notice that drag for the most part. You might, if you've got your hair down, you might notice your hair getting swept back. If you've got an open coat or jacket, the flaps of that may swing out. And that's drag, but it doesn't really have a measurable effect on your ability to move. So a lot of times we will ignore the drag exerted by the atmosphere unless we can see a measurable, marked difference that it's creating in the way the object is interacting. For example, something going really fast. Okay, so we're going to ignore it for the most part, but something moving fast or something that's extremely light. If I drop a feather or I drop a piece of paper, okay, you can see the drag that the air is exerting on that the atmosphere is exerting. So we can't ignore drag there. Okay, likewise, when you're driving really fast or if you're running, right now we've got baseball, softball, and track going. When you guys are running and the wind is blowing, you can tell that there is drag. When you're driving in your car, you can feel the drag. Okay, if you stick your hand out the window, that's drag. So things that are moving really fast, drag is not negligible. It is having a measurable effect. And drag that is being caused by water is always a measurable effect. Okay, it's never going to be something that we can ignore. So if there's water, if you've got something moving through the water, you can't ignore the drag. Lift, I mean, basically anything with an airfoil is going to experience lift. Anything that flies, planes, gliders, helicopters, the space shuttle, and probably something that I've forgotten about, fighter jets, they're going to have lift. The thing here I want to mention, Indy race cars, those are the ones that go really, really, really fast. They have inverted airfoils on the front end of the car. We talked about them earlier. So they actually do experience lift, but that lift is down instead of up because it's pulling them down and holding them onto the road because they're going far faster than most planes do when those planes are trying to take off. So if they come up over a hill, they can easily go airborne. That airfoil, by having it inverted on the front, pulls the front end of the car down so the car doesn't go airborne. So there is lift on Indy race cars, and it's down instead of up. So that might be something to keep in mind. Okay, then we have our 5 contact forces that we talked about. This is what we've actually been drawing free body diagrams for, so I'm going to go through these a little faster. Normal force, anytime you have 2 solid objects in contact. Water does not count here. Ice does. Water does not. It has to be 2 solids. Okay, there is a normal force. Okay, that normal force is perpendicular to the surface of contact and must be directed toward the thing that we're discussing. Okay, so for example, if I say a chair sitting on the floor, okay, that chair is in contact with the floor. It's sitting on top of the floor. There is a normal force that the floor is exerting on the chair to hold it up. So that would be an upward force. Most of the time, normal force is going to be pretty straightforward. We're not going to do too much with the weird, funky circumstance like the roller coaster that we talked about in the previous video. But I want to make sure that you've seen those. You know, it doesn't have to be up. It's usually going to be up, but it doesn't have to be. Friction, again, 2 solid objects in contact. It has to be, again, solids. Liquids don't count. There's going to be potential for friction. The chair sitting on the floor doesn't have friction. There's no friction that we have to deal with there. Now, if I start pushing that chair, I'm trying to act like I'm pushing it, but you can't see. If I start pushing that chair, then now there's movement or attempted movement. Okay, so now there's friction. There has to be either movement taking place or something has to be trying to move. Now, that could be because something's pushing on it, could be because it's sitting on a slope and it's trying to slide down the slope, but there has to be either movement or attempted movement for friction to be present. And it always opposes the motion. Now, why specifically does it have to be 2 solid objects? Why can't it be a liquid? Well, if it's a liquid, it's drag, not friction. Remember, drag is a subtype of friction. It's air friction or fluid friction. Okay? Okay, then we have buoyancy force. Anything, again, just like drag, anything immersed in a fluid is going to be experiencing a buoyancy force. But again, it's not always measurable. Right now, I'm standing in my classroom. I am immersed in a fluid. I'm immersed in the atmosphere. It's exerting a buoyancy force on me, and we could calculate exactly what that buoyancy force is. But it's so small, again, kind of like drag, that we don't really care about it unless the object is really, really light or if it's moving in certain different fluids. So any object immersed is experiencing buoyancy, but again, we're going to ignore it unless there's a measurable effect. Extremely light objects, like a balloon. Okay, good Lord, I'm blanking. There was something else I wanted to mention here, but I can't remember what it is. Something light getting dropped, there's going to be a buoyancy force on that has to be accounted for. All objects in water, again, measurable effect. Water has an extremely high buoyancy force. So even something sitting on the bottom of the ocean, even the Titanic, you would have to account for the fact there is a buoyancy force there. Okay? So anything immersed in water, buoyancy force. Last 2, tension and applied force. Tension is really easy to spot. If there is any kind of string or cable or cord that's connecting something to something else, then there's going to be tension. With an asterisk, that cord has to be tight. Okay? For example, if I let go of a balloon, okay, if I'm holding onto a balloon, there is tension in that string. When I let go of the balloon, that tension goes away. I'm no longer exerting a force on that balloon. The tension is gone. So the tension goes away unless that is connected to something. That string is tight when I'm holding on to the other end of the string. But when I let it go, the tension goes away. Now, there are some things that generate tension that are very heavy, like a chain. If you think about an anchor chain, okay? Something like that, even if it's not connected to something, I guess technically it's connected to an anchor, but even if you just held a chain, there is tension there. You don't have to calculate it, you don't have to quantify it, but there is tension there that's being exerted on whatever the thing that chain is attached to. So there is tension in circumstances like that. Even if the chain isn't technically tight, its weight is enough that there is a tension force. That's one that's not going to come up very often. Okay, and the last one is applied force. Anytime you are pushing on something, that's an applied force. You are exerting an applied force. And generally, there's going to be friction opposing that applied force. So if there's an applied force, there's probably also a friction force. There are circumstances where it could be something other than a push or a pull. I am going to make an effort to keep those to a minimum. We may have a couple spots where we call that something else. Hang on, my phone is going off. Okay, sorry about that. There may be some times where there is an applied force that we call something else. There are going to be times where we'll just say, ignore it, it's negligible. But for the most part, push or pull. I'm going to try to keep situations where it's not a push or a pull to a minimum in this class. And that's pretty much it. So worksheet 8.3a is the worksheet you need to fill out for all this. That is another graded worksheet. I think it's 20 points. It should be pretty quick. It's just the green text and the blue text you need to write. Remember, this stuff, not just the green, all of this stuff is stuff that you need to know or at least have a general idea of in order to do free body diagrams, which is what we're starting next. Okay, so hopefully this made sense, and that's pretty much it for this video. So I'm going to stop it here, and I'll see you in the next video.